So in the case of 17 oxygen, if I want to do the shell model spectroscopy, how do I proceed? First step. The first step is finding the closed core. In this case, it will be the 16 oxygen core. Next, the model space, where how many states do I consider? Suppose, let me take these two levels only, these two levels as the model space. So, this is my model space, this is the closed core space, and anything above this corresponds to the truncated space. Okay, so this is the very first step towards the configuration mixing shell model. Understand? This is the very first step. Next, what can I do? The next step is I have got only two levels, right? So let us name them phi 1 and phi 2. Now, when I am talking about this shell model procedure, you remember, right, that actually we have got the interaction potential V12. But in this case, what we will do, we will take P plus V0 and again we will add V0 minus V12. This is how we do the problem. So this is the shell model potential and this is the residual interaction part. So because of this residual interaction part, what will happen? These are shell model wave functions, you can say. Because of this component, they will be mixing among them. Now we have got two levels, so we will consider a 2 by 2 matrix. H11, H12, H21, H22. And this corresponds to this residual interaction components. The very existence of this off-diagonal element is because of the residual interactions. Okay? So this is the step. Next, I will be solving this matrix element, this determinant H11 minus lambda, H22 minus lambda, H12, H21. From here I will get the eigenvalues. Similarly, I can get the new eigenfunctions. Okay, eigenvalues are new eigenfunctions. So what is actually happening is that you can think of it like this. Because of the mixing, this was my initial phi 1, phi 2. Because of the mixing, there will be a separation among them. Now you can ask me, sir, why does this diagram look like this? Why doesn't it look like this? I mean, the levels after mixing they come close to each other. Now think about any natural procedure, any natural process. Whatever happens, what is the driving thing? To conserve energy, you can say. Okay, any process. If it is energetically possible, that will happen. Now in this case here, what is the result of the mixing between the two levels? One level becomes lower or it becomes more bound. Again, another becomes less bound. But the result is this thing. The result of mixing in this way is naturally to make one level more bound. Okay, and another level becomes less bound as a consequence, not the other way around. So this is not correct. This is the thing that we observe. Now this is the second step. And how much separation is there, this will be somewhat dependent on the eigenvalues. These are the eigenvalues, right? That it will be dependent on the H12, H21 elements. This will be dependent. Okay, so this is the second step. Next, we will compare these eigenvalues with the experimental data and see if it matches or not. Suppose it doesn't match, then I can tweak these off-diagonal elements, the delta admixture, to match with them. So this is the overall procedure of configuration mixing shell model. Just I have shown you for the case of 17 oxygen or so, right? Very basic idea. Same you can do for 18 oxygen. In that case, you will have 2 neutrons over here. and for the case of 18 oxygen, say 0 plus state, there you can have 0 plus state from here, here and here. So you can choose the model space, this, and above truncated space.